Alright guys, welcome to Applications of Integrals 05, Volumes with Cylindrical Shells. So in this lesson we're actually going to do the exact same volume problems that we did in the last few sections, but we're going to use the cylindrical shell method to solve them instead of the disk method. Okay, so here we go. Alright, so consider this problem. Find the volume of the solid created when the region created between, find the volume of the solid created when the region created between the curves y equals 4 minus x squared, which is this guy right here, y equals x squared, which is this guy right here, x equals 0, which is this guy right here, and x equals 1, which is this guy right here. Okay, so I'm going to erase those. Okay, and just so that we're clear, it's this region in here. Okay, so this region here. Okay, and we're going to revolve that around the y-axis, which is what's kind of weird about this problem. It doesn't feel normal to us to revolve that around the y-axis because it's 4 minus x squared and y equals x squared. So we feel like if this were revolved around the x-axis, that would be really easy, because then we would just go from 0 to 1, 4 minus x squared, y to y equals x squared, and we'd be good, right? But if we're revolving around the y-axis, it creates a problem, because now we have these disks here. We have a disk like this, we have a disk like this, sort of like that, and a disk like this, right? So these are the disks that we have, and that creates a problem, because these disks are not the same. This disk has a radius like this, okay, and that radius goes from the curve, and we have to write it in y, because remember, if we're revolving around the y-axis, and we're using the disk method says that we're going to be integrating in y. So we have to rewrite this in terms of y. So I'm going to switch the x over there and the y over here. And I'm going to get x equals square root 4 minus y. Right, plus or minus, and the minus would go over here and the plus would go over here. And so I would have the square root of 4 minus y minus 0. Right, and that would be the radius for this top part. But then in the middle, I'm not going all the way out to the curve, because the curve is all the way out here. But that's not my radius, right? My radius is here, which is sort of the pain in the rear end, right? So my radius here is 1 minus 0. And then if I'm here on this bottom part, my radius here is square root of y, right? So my radius here is square root of y to 0. So I actually have to split this up into 3 separate pieces, right? So, okay, so if I'm going, let's look at this top piece here. I'm going, remember we're doing this in y, which means we have to have y bounds, right? So I'm going from this point up to this point, right? And this point, well, that's where x equals 1 crosses y equals 4 minus x squared. So I plug in x equals 1, right? And I get, I'm having trouble writing here. Y equals 4 minus 1 squared, which is y equals 3, right? So this is 3. And up here, this is x equals 0, so that's 4, right? So I'm going to have pi times the integral from from 3, we just figured that out, from 3 to 4 of square root of 4 minus y squared dy. And then the second part, we have pi integral from, and then this point here, this is where x equals 1 meets y equals x squared. 1 squared is 1, so we're going from 1 to 3 of, and we're going from 1 to 0, so just 1 squared dy. And then this last part, pi, going from 0 to 1, to 0, really it is, of the square root of y squared dy. And so we have all three of these pieces, and we have to then add them up. And if you plug that into your calculator, I believe we actually get 3 pi. It actually comes out kind of nice. Right? But it leads us to the question, wouldn't it be nice if we could integrate this in x? I mean, I don't know if you can see this over all the other writing, but look, if I just go from here down, I'm going from 4 minus x squared to x squared. And here down, 4 minus x squared to x squared. 4 minus x squared to x squared. 4 minus x squared to x squared. Right? It would be really nice if we could just go from top to bottom instead of trying to go from right to left. So the idea here is that we want to try and integrate this in x instead of integrating this in y. But we don't have a choice if we're using the disk method. Which leads us to the shell method. The idea of the shell method is that it gives you a second option. The shell method says, okay, you don't want to integrate this in y, you want to integrate this in x? Use the shell method. And the shell method automatically switches your integration to the other thing. So if you had to integrate it in x, now the shell method would be integrating it in y. And if you had to integrate it in y, the shell method would allow you to integrate it in x. So what does the shell method do? The shell method creates a bunch of interlocking cylindrical shells. It's almost like the little Russian dolls, where you have the teeny tiny one inside the slightly bigger one, inside the slightly bigger one, inside the slightly bigger one, inside the slightly bigger one. It's the same idea. So I have one cylindrical shell here. I would have another one that would go from there to there, down to here. Right, so I'd have another one here. I would have a slightly skinnier, taller one here. Right? And they would all be infinitely skinny. We kind of want to think of almost like paper tubes, okay? That would interlock, that would fit together perfectly, right? So basically just literally thinking paper tubes. So take a piece of paper, roll it into a tube, and that would be what you would think of as a cylindrical shell. So it is just an infinitely thin shell. So we have the body of the thing, but we don't have a top, we don't have a bottom, and it's just almost like a surface area and an infinitely thin thickness. Okay? All right. So going back from all of this here, so we don't actually need to see all of these. No, not going back that far. Okay. So what we have here is you have your cylindrical shell, and your volume for that cylindrical shell, right? Remember, it's like a paper tube, so you have a surface area, right, times a thickness. It's kind of like you've got a piece of paper, and that piece of paper has a volume, but we don't really think of it as having much volume because it's so thin that it's kind of like the area of the paper times the teeny tiny thickness of the paper. Okay? So the surface area, we don't have a top and bottom, so we don't worry about the 2 pi r squared. We only worry about the 2 pi r h, and then the thickness, which is going to be, well, I'm going to call it t for now. Okay? So let's look at this radius here. The radius, right, is this right here, And we're integrating this in x, so we want to think about what is this in terms of x. Well, if this is the point on the curve, right, or we can think about it, right, the same radius would be right here, right? If this is the point on the curve, if I were to make a line right here, that point would be x comma y, right? So this distance from here to here is just x. So the radius is actually just x. And so we get 2 pi x. The height from here to here, maybe I should make that a different color, but the height is actually just, and very similar to what we did before when we did our area problems, is just going to be f of I guess f1 of x, we'll say, minus f2 of x. Right? We're going to subtract our two functions from each other, right? In this case, 4 minus x squared minus x squared, right? It's going to be our first function minus our second function. Just what we did when we did area, the exact same problem. Okay, so that's going to be height. And then t is going to be your thickness, and it's infinitely skinny, just like a piece of paper. So just like we did before with our discs, where we said there were infinitely thin discs, the thickness became dx. And so we're going to do the same thing there. Okay? So now what we're going to do is, let's highlight the region again. So the region is from here to there, is we're going to integrate this volume of one of our cylindrical shells over all of the cylindrical shells. And the cylindrical shells go from a radius of a really, really teeny tiny radius of 0 all the way out to the biggest possible radius would be right here. Right? That would be the biggest possible radius. And this would be the smallest radius, right? Would be right like that. So we're going to say that we're going to integrate it over all the radii. So we're going to have 2 pi. Okay, that's not a good color for this. Try that again. So we're gonna then integrate over, and I guess I shouldn't say over all the radii, but integrate over all the possible x's, right? Over the whole region. So integrate over region, right? And the region starts here at 0 and it ends at 1. So we're going to say, I'm going to put the 2 pi on the outside, and we're going to go from 0 to 1, and then we just have x, and we're going to go from the top, and the top, I kind of have these written backwards, but this top part is 4 minus x squared, okay? That would be the top, the bottom, which is x squared, so 4 minus x squared minus x squared, and then dx. And that's it. So we have 2 pi r h times thickness. And there's r, there's h, there's thickness. And if you put that in a calculator, you still get 3 pi. So it works out nicely. Alright. So hopefully that made some sense. Now where this really comes in handy is when you're revolving around a line that isn't an axis. When we're revolving around, for instance, the line x equals 4, which is right there. Okay. Alright, so find the volume of the solid created when the region created between the curves y equals 8 minus x squared, which is this top thing here, and y equals x squared, which is this bottom part here, around the line x equals 4. Okay, so it's kind of this eyeball looking thing here. And notice that that goes on both sides of the y-axis. Okay, we can figure out what those points are, right? We can say x squared equals 8 minus x squared. Add x squared to the other side, we get 2x squared equals 8. Divide by 2, x squared equals 4, x equals plus or minus 2. So we get over here, this is negative 2, and over here this is positive 2. Right? So we have both of those points there. Okay, so now we could try and do this in y, which is what we'd have to do, right? Anything parallel to the y-axis, we would integrate in y, but that would get really ugly. So let's try it with shells. So remember, we need 2 pi, radius, height, thickness, right? So the radius here is a little funny. So if we remember from the last problem, right, we said that the radius was x. And we said that because it was a point on the curve, and a point on the curve to there would be x, because that's how far, right, if I follow it down, right, it would be, that's x on the x-axis, right? But now if I look, the radius here, that's not x on the x-axis, that's 4. What's x on the x-axis? If I draw this point, this is x on the x-axis, right? If I follow it down, that would be where x would, right? That's how far x is, that's the point x comma y. And all the way across would be 4. So the radius is actually, right, if I make an arrow back, that would be the line 4 minus x, right? If it goes all the way back to the y-axis, it would be 4, and this part is x, so this part here is 4 minus x. Okay, so the radius, 4 minus x, and then we look at the height. So the height, let's do the height in brown. The height is from the top here, and not all the way to the x-axis, but just to the next curve, right? So like from here to here, or from here to here, right? So it goes from 8 minus x squared down to x squared. So that's the height. And then the thickness is always the same. The thickness is always dx. Alright, and we take the integral, 2 pi, and the integral is going to go from here to there, so from negative 2 to 2, and I got, I believe, 512 pi over 3. Random numbers. Okay. Alright. Nothing to it. Alright, next and last problem. Sorry about that, I left my last page of notes in the other room. Okay. So, the last piece of this, we're going to try revolving around something in the other direction. So, find the volume of the solid created when the region created between the curves y equals x squared, which is this guy right here, y equals 1, and y equals 2, is revolved around the line y equals negative 3, which is, you can see it right here. Okay? So now we're going in the opposite direction. So if we're revolving around y equals negative 3, now we're not going to work in dx, we're going to work in dy. We're going to integrate in y. Okay? And hopefully you can see it. We're going to have this funny looking shape in here. Okay? Okay. So, same idea. 2 pi r h thickness, right? Okay. So the radius is going to be, well, the radius would have been just something on the function going down to the axis, right? So that would have been something on the function going down to the axis. That would have been y, right? X goes this way, y goes this way. So the radius would have been y. Okay, this is the point x comma y goes down to here, that's y. But it's not that because it goes all the way down to here now. And if it goes all the way down to here, if this is y, this is 3 more, right? It's almost like y minus minus 3, or we could think of it as y plus 3, right? So we can think of it either as y and then plus 3 more, or go from top to bottom, and we always subtract what we're going down to, and we're going down to negative 3. So subtract the negative 3, or just think of it as it's y plus 3 more. So there's our radius. Right. I don't know if you can see that's an arrow, or at least it was an arrow. And now we look at the height. The height, we always go from right to left. Right, so the entire thing would be the height. Now it's tempting to say, well, that's x squared, but that whole thing is x squared. So how is it going from one function to another? Your clue should be that it is, in fact, it has to go from one function to another. This piece has to be different from this piece. So how is it different? Well, remember we're doing this in y, not in x, right? So if we're doing this in y and not in x, then we need to change this guy. So it's going to be, right, square root both sides, and never forget your plus or minus. So x equals plus or minus root y. So this side is root y, and this side is negative root y. So it's going from root y to negative root y. Okay? So it's going root y minus negative root y. Right? Okay, and then of course, so that's d. And then of course thickness, always the same. Well, I guess not exactly the same. It's not dx anymore, it's dy. Right? And then we integrate. 2 pi on the outside. And it's not going, we're not looking for an x value to an x value. We're looking for a y value to a y value. And that's easy enough. It's going from 1 to 2. Alright, and the reason I needed my notes, this is 9.752. It does not come out to a nice number at all, even close. So, there you go. Alright, so hopefully that makes sense, and if not, you can ask me about it in class, and that's it. So, there you go.